Hey everyone. Tonight we begin with something profound and quietly magnificent. The deepest places on Earth. Yes, beneath our feet and far below the ocean's surface lies a world so vast, so unexplored, that we know more about the surface of Mars than we do about the deepest parts of our own planet. And let me tell you, some of these places are breathtaking. Some are mysterious. All of them are humbling reminders of just how much of our world remains gently hidden from view. So before you settle in, take a moment to like the video if you're enjoying what we're exploring together, and let me know in the comments where you're listening from and what draws you to Earth's hidden depths. It's always fascinating to connect with fellow curious souls from around the world. Now, dim the lights if you can, maybe adjust your pillow, and let's descend together into the quiet mysteries that lie beneath. In a world where we've mapped every mountain peak and charted every coastline, the deepest places on Earth remain largely untouched, unexplored territories that exist in perpetual darkness, under crushing pressures, yet somehow still harbour life in the most extraordinary ways. Picture this. Right now, as you listen to these words, there are places on our planet where the pressure is over 1,000 times greater than what you're experiencing. Places where no sunlight has ever penetrated, where the temperature hovers just above freezing, and where the silence is so complete it's almost tangible. These are not distant alien worlds. They're here, beneath our oceans, carved into our continents, waiting patiently in the darkness. The story of Earth's deepest places begins with understanding that our planet is not the solid, unchanging sphere it might appear to be. Deep beneath the surface, massive tectonic plates drift slowly across a molten mantle, grinding against each other, sliding beneath one another, creating the very foundations for the extraordinary depths we're about to explore together. When these colossal plates converge, something remarkable happens. The denser, older oceanic crust gets forced downward beneath the lighter continental crust in a process called subduction. It's a dance that's been going on for hundreds of millions of years. And it's this ancient choreography that has carved out the deepest trenches in our oceans, creating underwater canyons so vast that entire mountain ranges could disappear within them without a trace. But Earth's deepest places aren't limited to the ocean floor. Beneath our continents, water has been quietly working for millennia, dissolving limestone and carving out cave systems that plunge thousands of meters into the Earth's crust. These subterranean cathedrals exist in complete darkness, their passages filled with the gentle sound of dripping water and the occasional whisper of underground streams finding their way through stone. Let's begin our journey downward with the deepest places we can actually visit on land. The cave systems that represent humanity's furthest reach into the solid Earth beneath our feet. These are not the tourist caves with walkways and electric lights, but wild, untamed spaces where explorers spend weeks underground, rappelling down vertical shafts and crawling through passages barely wider than their bodies. In the Republic of Abkhazia, a disputed region along the eastern shore of the Black Sea, lies a cave system so deep it holds the current world record for subterranean depth. Veryovkina Cave, discovered in 1968, by Soviet speleologists who had no idea of the true magnitude of what they'd found, descends an astounding 2,209 meters into the Earth. That's nearly 7,300 feet straight down, deeper than 6 Empire State Buildings stacked on top of each other. The entrance to Veryovkina sits 2,285 meters above sea level in the Arabica Massif, part of the Western Caucasus mountain range. It's a modest opening, just 3 by 4 meters across, giving no hint of the vertical labyrinth that awaits below. The first shaft drops 32 meters before the cave begins its true descent into darkness. What makes Veryovkina particularly remarkable is how it descends. Unlike horizontal cave systems that meander through hillsides, this cave goes almost straight down, a series of vertical shafts connected by brief horizontal passages. Starting around 800 meters down, water begins to flow through the passages, creating a constant mist that chills explorers to the bone and makes every surface slippery with condensation. The exploration of Veryovkina has been a decades-long endeavor requiring extraordinary dedication from Russian speleologists. Using a series of underground camps, it takes expedition members more than 4 days to reach the deepest known point, and roughly the same time to return to the surface. This means spending at least a week in an environment of perpetual darkness, where the only sounds are the echo of dripping water and the distant murmur of underground streams. The cave goes deeper still. At the bottom, 2,209 meters down, lies a water-filled passage called a siphon, where the cave continues but is completely flooded. Recent expeditions have used underwater drones to explore these submerged sections, revealing that the cave system extends even further into the earth, though the exact depth remains a mystery waiting to be solved. The conditions inside Veryovkina are extreme in ways that challenge human endurance. The temperature remains just above freezing throughout the year, and the humidity approaches 100%. Explorers must navigate through water and mud-choked passages, rappelling down thousands of feet of rope in sections where a single equipment failure could prove fatal. The perpetual darkness plays tricks on the human circadian rhythm, and explorers often find themselves working at night and sleeping during the day even when they return to the surface. Yet Veryovkina may not hold its record for much longer. In Mexico, Sistema Cheve presents a tantalizing possibility of even greater depths. Located in Oaxaca, this cave system has the potential to become the deepest cave on Earth, though much of it remains unexplored. In 1990, explorers dumped green dye into the stream flowing into Cheve's entrance and discovered the colored water emerging near the mountain's base, some 1.6 miles down from the cave's highest known entrance. If humans could navigate the full length that water travels, Cheve would claim the record by almost a quarter mile. The exploration of Sistema Cheve represents one of the greatest challenges in modern speleology. The cave is a three-dimensional maze within a mountain, with passages that flood during certain seasons and sections that require technical diving skills to navigate. Expeditions to Cheve are measured not in days, but in weeks, with teams establishing multiple underground camps and using advanced diving equipment to explore the deepest, water-filled sections. These deep cave systems exist because of a simple but powerful geological process. Over millions of years, slightly acidic groundwater seeps through limestone, gradually dissolving the rock and creating ever larger passages. The process is incredibly slow by human standards, but relentless by geological ones. Drop by drop, the water carves out chambers and tunnels, creating underground landscapes as varied and beautiful as anything on the surface. What's remarkable about these cave systems is that they represent some of the most stable environments on Earth. While the surface world experiences daily temperature swings and seasonal changes, the deep caves maintain constant conditions year-round. The temperature at any given depth remains virtually unchanged, creating microenvironments that have persisted for thousands of years. But caves, no matter how deep, represent just the beginning of our planet's hidden depths. To find Earth's truly deepest places, we must leave the solid ground behind and venture into the realm of water, where depth takes on an entirely different meaning. Freshwater lakes, carved by glaciers and fed by underground springs, create some of the deepest water bodies on our continents. Lake Baikal in Siberia, often called the Galapagos of Russia, reaches a maximum depth of 1,642 meters. This ancient lake, formed in a rift valley over 25 million years ago, contains 20% of the world's unfrozen fresh water and hosts species found nowhere else on Earth. The depth of Lake Baikal is the result of tectonic forces that continue to this day. The Baikal Rift Zone is slowly pulling apart, creating a depression that fills with water from hundreds of tributary streams and underground springs. The lake is so deep that its bottom lies 1,100 186 meters below sea level, making it not just the deepest freshwater lake, but also one of the lowest points on any continent. In winter, Lake Baikal freezes to a depth of over a meter, creating a crystal-clear ice surface that allows visitors to peer down into the depths below. But even this remarkable lake, vast and ancient as it is, pales in comparison to the true depth champions of our planet, the oceanic trenches that slice through the seafloor like massive underwater canyons. The ocean covers more than 70% of Earth's surface, yet we've explored less than 5% of this vast underwater realm. Most of the ocean floor lies at depths of 3 to 4 kilometers below sea level, but in certain locations, the seafloor plunges much deeper, creating trenches that represent some of the most extreme environments on our planet. These oceanic trenches are not randomly distributed across the globe. They follow the boundaries where tectonic plates meet, marking the locations where one massive piece of Earth's crust slides beneath another. There are approximately 50,000 kilometers of oceanic trenches worldwide, mostly ringing the Pacific Ocean in what geologists call the Ring of Fire. The formation of an oceanic trench begins when two tectonic plates converge. The denser, older oceanic crust gets forced downward beneath the lighter plate in the subduction process we mentioned earlier. As this happens, the edge of the overriding plate gets bent downward, creating a depression that can extend for thousands of kilometers and reach depths that dwarf any terrestrial canyon. These trenches are typically 50 to 100 kilometers wide and 3 to 4 kilometers below the level of the surrounding ocean floor. But their length is what truly impresses, with some extending for thousands of kilometers across the ocean basins. The Peru-Chile Trench runs for over 5,000 kilometers along the western coast of South America, while the Aleutian Trench extends for more than 3,000 kilometers from Alaska to Russia. But for sheer depth, no trench on Earth compares to the Mariana Trench in the western Pacific Ocean. Located about 200 kilometers east of the Mariana Islands, this crescent-shaped depression measures about 2,550 kilometers in length and 69 kilometers in width. It represents the deepest part of the world's oceans and, by extension, the deepest accessible place on Earth. The Mariana Trench formed where the Pacific Plate, carrying some of the oldest oceanic crust on Earth, slides beneath the smaller Mariana Plate. This oceanic crust is up to 170 million years old, making it cooler and denser than younger crust, which explains why it sinks so readily beneath the overriding plate. But even within this deepest of trenches, there is a place that stands apart from all others. At the southern end of the Mariana Trench lies a small depression known as Challenger Deep, the deepest known point in Earth's oceans and the closest thing to an alien world that exists on our own planet. The name Challenger Deep comes from the British Royal Navy survey, ship HMS Challenger 2, which first measured the depth of this location during expeditions in the early 1950s. But it was decades before humans could actually visit this remote and hostile environment, and the story of that first journey represents one of the greatest adventures in the history of exploration. History of exploration. On January 23, 1960, two men descended into Challenger Deep aboard a vessel that looked more like a steel sphere with propellers than a conventional submarine. The French-built bathyscaphe Trieste, operated by the US Navy, carried Swiss ocean engineer Jacques Piccard and American naval officer Don Walsh on what would become one of the most remarkable journeys in human history. The descent took nearly 5 hours, a slow, methodical journey through layers of ocean that grew progressively darker and more alien with each passing kilometer. At a depth of about 1 kilometer, the last traces of sunlight disappeared completely, leaving the two explorers in a darkness so absolute it seemed to have weight and substance. And the water temperature dropped steadily as they descended, eventually reaching just above freezing at the bottom. As the Trieste sank deeper, the pressure outside the vessel increased at a rate that defies easy comprehension. For every 10 meters of descent, the pressure increased by approximately 1 atmosphere. By the time they reached the bottom at 10,916 meters below sea level, the pressure had reached over 1,000 times what we experience at the surface. To put this in perspective, if you could somehow transport a person to that depth without protection, their body would be compressed to a fraction of its normal size in an instant. Yet Piccard and Walsh, protected by the Trieste's thick steel sphere, reached the bottom safely and made a discovery that changed our understanding of life on Earth. Even at this crushing depth, in perpetual darkness and near freezing temperatures, they observed what appeared to be a flatfish swimming past their porthole. Life, it seemed, had found a way to exist even in the most extreme environment our planet has to offer. The next person to visit Challenger Deep would not arrive for more than 50 years. In March 2012, filmmaker James Cameron piloted the specially designed submersible deep-sea Challenger to a depth of 10,898 meters, establishing a new record for solo descent. Cameron's journey provided the first high-definition footage of this alien landscape, revealing a barren seafloor covered in fine sediment, punctuated by strange rock formations and the occasional deep-sea creature. But it was Victor Vescovo's descent in 2019 that truly opened our eyes to the deepest place on Earth. Using the advanced submersible limiting factor, Vescovo reached a new record depth of 10,928 meters and spent hours exploring the bottom of Challenger Deep. His multiple dives revealed a landscape more varied and active than previously imagined, with rocky outcrops, sediment clouds stirred up by bottom currents, and a surprising diversity of life forms adapted to these extreme conditions. The pressure at the bottom of Challenger Deep is equivalent to having about 50 jumbo jets pressing down on every square meter of surface. It's a force so immense that it would instantly crush any conventional submarine. Yet specialized deep-sea creatures thrive in this environment. Their bodies have evolved unique adaptations, with proteins that remain stable under extreme pressure, and cellular structures that can withstand forces that would destroy surface-dwelling organisms. The temperature at these depths hovers around 2 degrees Celsius, just above the freezing point of seawater. This near-freezing temperature is maintained by the thermal properties of the deep ocean, where cold polar waters sink and spread across the ocean floor. The water itself moves in slow, predictable patterns, carrying dissolved minerals and nutrients from the surface world down into the abyss. Sound behaves differently in the deep ocean than it does at the surface. In 2015, scientists deployed a specialized hydrophone into Challenger Deep, designed to withstand the crushing pressure 7 miles below the surface. The titanium shell device recorded a surprisingly rich acoustic environment. Even in this remote location, the sounds of earthquakes, typhoons, and distant baleen whales could be detected, along with the mechanical noises of ships passing thousands of meters above. The water in Challenger Deep is remarkably clear, though no sunlight penetrates to illuminate it. Without photosynthesis, the entire ecosystem depends on a process called chemosynthesis, where bacteria convert chemicals seeping from the Earth's crust into energy. These bacteria form the base of a food chain that supports tube worms, strange fish, and other creatures that seem almost alien in their adaptations to this extreme environment. The sediment on the bottom of Challenger Deep tells a story spanning millions of years. Fine particles of clay and the remains of microscopic organisms have settled here from the water column above, creating layers that preserve a record of Earth's climate history. Mixed within this sediment are minerals and metals that have precipitated from the water over geological time, creating deposits of scientific and potentially economic interest. Recent expeditions have revealed that even this most remote location on Earth shows signs of human impact. Researchers have found microplastics and chemical pollutants in the deepest parts of the trench, carried there by ocean currents and the settling of particles from the surface. The discovery serves as a sobering reminder that human activity affects even the most distant corners of our planet. The Mariana Trench extends far beyond just Challenger Deep, encompassing an ecosystem that spans different depth zones, each with its own unique characteristics and inhabitants. The Hadal Zone, named for Hades, the Greek underworld, encompasses all ocean depths greater than 6,000 meters. This zone, representing less than 1% of the ocean's volume, harbors some of the most specialized life forms on Earth. At depths between 6 and 8,000 meters, the seafloor supports communities of amphipods, small crustaceans that have adapted to the extreme pressure and cold. These creatures feed on organic matter that drifts down from the upper ocean, creating a connection between the surface world and the deepest depths. Some of these amphipods grow to remarkable sizes, with specimens over 30 centimeters long discovered in various Pacific trenches. Deeper still, between 8 and 10,000 meters, the diversity of life decreases but doesn't disappear entirely. Xenophyophores, single-celled organisms that can grow to the size of dinner plates, create delicate structures on the seafloor. These giants of the microscopic world play important roles in the deep sea ecosystem, providing habitat for smaller organisms and helping to process organic matter that settles from above. The deepest fish ever recorded on video was discovered at 8,336 meters in the Izu-Ogasawara Trench, a juvenile snailfish that seemed to glide effortlessly through the water despite the crushing pressure. These fish have evolved specialized proteins and cellular structures that allow them to function at depths where conventional fish cannot survive. Their discovery pushes the boundaries of where we expect to find vertebrate life on our planet. Throughout the Pacific Ocean, similar trenches create islands of extreme depth in the vast ocean basins. The Tonga Trench in the South Pacific reaches depths of nearly 11,000 meters, making it the second deepest point on Earth. Here, the Pacific Plate subducts beneath the Indo-Australian Plate at a faster rate than anywhere else on the planet, creating a dynamic environment of earthquakes and volcanic activity. The Philippine Trench, stretching for over 800 kilometers through the Western Pacific, reaches maximum depths of over 10,000 meters. This relatively young trench, formed only 8 to 9 million years ago, represents one of the most seismically active regions on Earth. The convergence of tectonic plates here generates frequent earthquakes that ripple across the Pacific, sometimes triggering tsunamis that affect coastlines thousands of kilometers away. In the Atlantic Ocean, the Puerto Rico Trench marks the deepest point in that ocean basin. Located northwest of Puerto Rico, this trench reaches depths of over 8,000 meters at a point known as Milwaukee Deep, named after the USS Milwaukee, the first ship to discover and measure its depth in 1939. The Puerto Rico Trench formed at the boundary between the North American and Caribbean plates, creating a zone of active tectonics that continues to shape the seafloor today. Each of these trenches represents a unique laboratory for studying life under extreme conditions. The isolation of deep-sea environments has led to the evolution of endemic species found nowhere else on Earth. In the Japan Trench, researchers have discovered bacteria that can survive pressures exceeding 1,000 atmospheres, while in the Peru-Chile Trench, unique species of amphipods have evolved to thrive in the oxygen-poor waters that characterize parts of the Pacific Deep Sea. The exploration of these deep ocean trenches requires technology that pushes the boundaries of engineering and material science. The vessels that carry humans to these depths must be constructed from specially designed materials that can withstand pressures that would crush conventional submarines like tin cans. The viewing ports are made from acrylic spheres several inches thick, while the hull itself is typically constructed from titanium or specialized steel alloys. Life support systems for deep-sea exploration present unique challenges. The vessels must carry enough oxygen for extended missions while removing carbon dioxide and maintaining comfortable temperatures for the crew. Emergency systems must be designed to function under extreme pressure, and communication with the surface requires specialized equipment that can transmit through thousands of meters of seawater. The descent to the deepest parts of the ocean is a journey through distinct zones, each with its own characteristics and inhabitants. The sunlight zone, extending to about 200 meters below the surface, supports most of the ocean's photosynthetic activity. Below this lies the twilight zone, where the last traces of sunlight fade away and bioluminescence becomes the primary source of illumination. The midnight zone, beginning at about 1,000 meters depth, encompasses the vast majority of the ocean's volume. Here, temperatures drop to near freezing and pressure increases dramatically, yet life persists in forms adapted to these challenging conditions. Giant squid patrol these depths, while deep-sea fish with luminous lures hunt in the perpetual darkness. Below 4,000 meters lies the abyssal zone, where the seafloor spreads across vast underwater plains punctuated by underwater mountains and volcanic vents. The pressure here exceeds 400 times that at sea level, and temperatures remain just above freezing year-round. Yet even in this extreme environment, life flourishes in forms that seem almost alien to surface dwellers. The Hadal Zone, encompassing the deepest trenches, represents the final frontier of Earth's biosphere. Here, pressure exceeds 1,000 times that at the surface, and specialized organisms have evolved unique biochemistry that allows them to function under conditions that would be instantly lethal to most life forms. The study of these extreme organisms provides insights not only into the limits of life on Earth, but also into the potential for life in extreme environments elsewhere in the universe. Recent advances in deep-sea exploration technology have revolutionized our understanding of these extreme environments. Autonomous underwater vehicles equipped with high-definition cameras and sophisticated sensors can now spend months mapping the seafloor and studying deep-sea ecosystems without human intervention. These robotic explorers have revealed underwater mountain ranges, vast fields of hydrothermal vents, and ecosystems based on chemosynthesis rather than photosynthesis. The discovery of hydrothermal vents in the deep ocean has opened an entirely new chapter in our understanding of life on Earth. These underwater geysers, where superheated water rich in minerals erupts from the sea floor, support ecosystems that derive their energy from chemical reactions rather than sunlight. Giant tube worms, some growing to lengths of over 2 meters, cluster around these vents, hosting symbiotic bacteria that convert the chemicals in the vent water into usable energy. The study of deep-sea hydrothermal vents has implications far beyond marine biology. The unique chemistry of these environments may provide clues to how life first emerged on Earth, as the conditions around vents share similarities with the primordial environment in which life is thought to have originated. The discovery that complex ecosystems can thrive without sunlight has also expanded our conception of where life might exist elsewhere in the solar system. Deep-sea mining has emerged as a potential new frontier, as the extreme depths harbor valuable minerals and metals concentrated by geological processes over millions of years. Polymetallic nodules scattered across the abyssal seafloor contain manganese, nickel, cobalt, and other elements essential for modern technology. However, the environmental impact of deep-sea mining remains poorly understood, and concerns about disrupting these fragile ecosystems have led to calls for careful regulation of such activities. The deep ocean plays a crucial role in Earth's climate system, acting as a vast reservoir for heat and carbon dioxide. Cold, dense water formed in polar regions sinks to the deep ocean and spreads across the globe, carrying dissolved gases and nutrients that support life throughout the water column. This thermohaline circulation, sometimes called the ocean's conveyor belt, helps regulate global climate by distributing heat and influencing weather patterns worldwide. Climate change is beginning to affect even the deepest parts of the ocean. As surface waters warm and become more acidic due to increased carbon dioxide levels, these changes gradually propagate into the deep sea. The deep ocean's role as a carbon sink means that it absorbs much of the excess carbon dioxide produced by human activities. But this process is slowly altering the chemistry of deep-sea environments in ways that are only beginning to be understood. The exploration of Earth's deepest places continues to yield surprises that challenge our understanding of life and geology. Recent discoveries include vast underwater rivers flowing along the ocean floor, deep-sea lakes of brine that are denser than the surrounding seawater, and entire ecosystems thriving in the sediments beneath the seafloor. Each new expedition reveals that the deep ocean is far more dynamic and diverse than previously imagined. As we push deeper into Earth's most extreme environments, we're discovering that the boundaries between geology and biology are often blurred. Microorganisms live within the rocks of the seafloor itself, surviving on energy from radioactive decay and chemical reactions within the Earth's crust. These subsurface biospheres may contain more biomass than all surface ecosystems combined, representing a hidden world of life that exists entirely independent of the sun's energy. The deepest places on Earth serve as natural laboratories for understanding how life adapts to extreme conditions. The proteins and enzymes that allow deep-sea organisms to function under crushing pressure have potential applications in biotechnology and medicine. The study of how these organisms survive without sunlight may provide insights relevant to the search for life on other worlds, where similar extreme conditions might exist. Perhaps most remarkably, the exploration of Earth's deepest places reminds us how much of our own planet remains unknown and unexplored. We have better maps of the surface of Mars than we do of our own ocean floor, and each expedition to the deep sea reveals new species, new ecosystems, and new geological features that expand our understanding of Earth's complexity and beauty. In the quiet darkness of the deep ocean trenches, in the still air of the deepest caves, life persists in forms that speak to the remarkable adaptability and resilience of biological systems. These hidden worlds, existing in perpetual night beneath crushing pressure, or in the silent chambers carved by ancient waters, remind us that Earth is still a planet of mysteries, still capable of surprising us with its hidden depths and secret places. The deepest places on Earth exist not as empty voids, but as thriving ecosystems, complex geological systems, and frontiers of scientific discovery. They represent the ultimate expression of our planet's creative forces, where extreme conditions have shaped life into forms so specialized and remarkable that they seem to belong to another world entirely. As we continue to explore these hidden depths, we're reminded that most of our planet exists in peaceful darkness, in spaces where time moves differently and life follows rhythms older than human civilization. In these quiet places, removed from the bustling activity of the surface world, Earth's deeper nature reveals itself in forms both alien and beautiful, mysterious yet ultimately part of the same planetary system that sustains all life as we know it. The profound silence of these deepest places extends far beyond what we might imagine from our surface-dwelling perspective. In the deepest ocean trenches, sound travels differently than it does in the world above. The density of water under extreme pressure creates an acoustic environment where certain frequencies can travel for thousands of kilometers, while others are absorbed within meters of their source. Scientists have discovered that whales, those gentle giants of the surface waters, can sometimes be heard even in the deepest parts of the ocean. Their low-frequency calls, produced thousands of meters above, penetrate down through the water column like whispered messages from another world. These sounds arrive at the bottom of trenches as faint echoes of life from the sunlit realm above, creating an invisible connection between the surface and the abyss. The creatures that inhabit these deepest places have evolved remarkable ways of creating their own light in a world where no sunlight has ever penetrated. Bioluminescence, the gentle glow produced by living organisms, becomes the primary source of illumination in the deep. Bacteria, jellyfish, and deep-sea fish create patterns of light that serve as communication, navigation, and hunting tools in the eternal darkness. These biological light displays are nothing like the harsh artificial lighting of our surface world. Instead, they produce soft, ethereal glows in blues and greens, colors that travel furthest through the dense water. A deep-sea jellyfish drifting through the Hadal zone might pulse with gentle rhythms of light, creating a living constellation in the darkness. These displays are brief and purposeful, conserving energy in an environment where every calorie must be carefully managed. The movement of water itself in the deepest places follows patterns that have remained unchanged for thousands of years. Deep ocean currents, driven by differences in temperature and salinity, create a slow but constant circulation that carries nutrients and dissolved gases throughout the abyssal depths. These currents move at speeds measured in centimeters per day, creating a gentle, persistent flow that shapes the seafloor over geological time. In the deepest trenches, the water often forms layers with slightly different temperatures and chemical compositions. These layers can persist for centuries, creating distinct environments within the same vertical water column. A deep-sea creature might spend its entire life within one of these layers, adapted to its specific temperature and chemical conditions, never venturing into the layer just a few meters above or below. The sediments that accumulate on the floor of the deepest places tell stories that span millions of years. Each layer represents a different era in Earth's history, preserving microscopic fossils, volcanic ash from ancient eruptions, and even cosmic dust from meteorite impacts. The rate of sedimentation in these depths is extraordinarily slow, with some layers taking thousands of years to accumulate just a few centimeters of thickness. Within this ancient sediment, life continues in forms so small they're invisible to the naked eye, but so numerous they may represent some of the largest populations of living organisms on Earth. These subsurface microbes live in the spaces between sediment grains, deriving energy from chemical reactions and radioactive decay. They reproduce slowly, with some individual cells potentially living for thousands of years in a state of near-suspended animation. The pressure in these deepest places affects not just living organisms, but the very rocks and minerals of the sea floor. Under such extreme conditions, water itself behaves differently, becoming denser and less compressible. The rocks of the seafloor undergo slow but constant changes as minerals recrystallize under pressure, creating new compounds that exist nowhere else on Earth. Hydrothermal vents in the deepest trenches create oases of warmth and chemical activity in the otherwise cold and stable deep-sea environment. These underwater springs, where water heated by the Earth's interior emerges from cracks in the seafloor, support some of the most unique ecosystems on our planet. The water emerging from these vents can reach temperatures of several hundred degrees Celsius, but it cools rapidly as it mixes with the near-freezing surrounding seawater. The chemistry of hydrothermal vent water is unlike anything found elsewhere on Earth. Rich in hydrogen sulfide, methane, and various metals, this water would be toxic to most surface life. Yet specialized bacteria thrive in this environment, using the chemical energy to produce organic compounds in a process completely independent of photosynthesis. These bacteria form the foundation of food webs that include tube worms, clams, and crabs, all uniquely adapted to life around the vents. The discovery of hydrothermal vent ecosystems in the 1970s revolutionized our understanding of where life could exist. Before this discovery, it was assumed that all life on Earth ultimately depended on energy from the sun. The revelation that complex ecosystems could thrive in complete darkness, deriving energy from chemical processes within the Earth itself, opened new possibilities for understanding life, not just in Earth's depths, but potentially on other worlds. Some hydrothermal vents in the deepest parts of the ocean have been active for thousands of years, creating stable environments that have allowed unique species to evolve and thrive. The giant tube worms that cluster around these vents can live for decades, growing slowly in the nutrient-rich environment. These creatures have no mouth or digestive system in the conventional sense, instead hosting symbiotic bacteria within their bodies that convert the vent chemicals into usable nutrients. The exploration of these deepest places requires not just advanced technology, but also a different understanding of time and space. Missions to the deepest trenches are planned years in advance, with every detail carefully considered. The journey to the bottom can take hours, and once there, every moment must be used efficiently because the return trip is equally long and the window for exploration is limited by the life support systems of the submersible. The humans who venture into these depths describe an experience that transcends ordinary exploration. The descent through thousands of meters of water creates a meditative state, a gradual transition from the familiar world of the surface to an environment so alien it seems to belong to another planet. The pressure hull of the submersible becomes a tiny bubble of surface conditions, a fragile sanctuary carrying its occupants through pressures that would be instantly fatal. As explorers descend through the water column, they pass through distinct zones, each with its own character and inhabitants. The last traces of sunlight fade away at depths of less than 200 meters, but bioluminescent organisms create a different kind of illumination that continues much deeper. The transition from the twilight zone to the midnight zone is gradual, marked not by any sudden change but by a slow intensification of the darkness and cold. The seafloor of the deepest trenches, when finally reached, often appears as a vast, featureless plain covered in fine sediment, but closer inspection reveals a landscape of subtle hills and valleys, created by underwater currents and the slow accumulation of material from above. Strange rock formations, created by chemical precipitation or ancient lava flows, punctuate these sediment plains, providing habitat for the sparse but specialized life forms that call these depths home. The silence in these deepest places is not the absence of sound, but rather a different quality of acoustic experience. The crushing pressure affects how sound waves travel, creating an environment where even small sounds can seem magnified while others are completely absorbed. The gentle creaking of a submersible's hull under pressure becomes a constant companion, a reminder of the immense forces at work in these depths. Temperature in the deepest places remains remarkably constant, hovering just above the freezing point of seawater throughout the year. This thermal stability, combined with the constant pressure and darkness, creates one of the most unchanging environments on Earth. Seasonal variations that drive so much of surface life are completely absent here, replaced by geological rhythms that operate on timescales of thousands or millions of years. The water itself in these depths is ancient, some of it having been isolated from the surface for centuries. This deep water carries dissolved minerals and gases that tell stories of its journey through the world's oceans. Oxygen levels are lower than at the surface, but sufficient to support the specialized life forms that have adapted to these conditions. Carbon dioxide, absorbed from the atmosphere centuries ago, makes this deep water slightly more acidic than surface waters. The creatures that live in the deepest places have evolved remarkable adaptations that allow them to thrive under conditions that would be instantly lethal to surface-dwelling organisms. Their cell membranes are composed of specialized fats that remain flexible under extreme pressure, while their proteins are structured to maintain their function despite the crushing forces. Some deep-sea fish have gas-filled swim bladders that would normally be compressed to nothing under such pressure, but they've evolved ways to maintain neutral buoyancy even at these extreme depths. The reproductive strategies of deep-sea organisms reflect the challenges of life in these isolated environments. Many deep-sea species have evolved to reproduce slowly but steadily, with some organisms having lifespans measured in decades or even centuries. The scarcity of food and the difficulty of finding mates in the vast darkness has led to unique adaptations, including bioluminescent displays for mate attraction and the ability to survive long periods without feeding. Food webs in the deepest places are unlike those anywhere else on Earth. With no photosynthesis possible in the eternal darkness, all energy must come from above in the form of marine snow, the gentle rain of organic particles that drifts down from the surface waters. This marine snow consists of dead plankton, fecal pellets, and other organic debris that slowly sinks through the water column, providing the primary energy source for deep-sea ecosystems. The journey of marine snow from surface to seafloor can take weeks or months, during which much of it is consumed or decomposed by organisms in the upper layers of the ocean. By the time this organic material reaches the deepest trenches, it has been processed and reprocessed many times, becoming a concentrated source of nutrients that supports the sparse but specialized communities of the deep. Some of the most remarkable discoveries in the deepest places have come from the study of how life adapts to extreme conditions. Bacteria found in the deepest trenches have evolved enzymes that function under pressures that would denature most proteins. These pressure-adapted enzymes have potential applications in biotechnology and medicine, offering insights into how biological systems can be engineered to function under extreme conditions. The study of deep-sea organisms has also revealed new insights into the aging process and longevity. Many deep-sea creatures live much longer than their shallow water relatives, possibly due to the stable conditions and slow metabolic rates that characterize life in the depths. Some deep-sea clams and tube worms are thought to live for hundreds of years, growing slowly but steadily in the nutrient-poor environment. The geological processes that create and maintain the deepest places operate on timescales that dwarf human experience. The subduction zones that form oceanic trenches have been active for millions of years, slowly recycling oceanic crust back into the Earth's interior. This process not only creates the deepest places on Earth, but also plays a crucial role in regulating the planet's climate by controlling the exchange of carbon between the surface and the deep Earth. Earthquakes in the deepest places can be among the most powerful on Earth, generated by the immense forces involved in subduction. These deep earthquakes often occur at depths of several hundred kilometers below the seafloor, in the descending slab of oceanic crust. The energy released by these events can be felt across entire ocean basins, and the largest ones can trigger tsunamis that affect coastlines thousands of kilometers away. The volcanic activity associated with subduction zones creates underwater mountain ranges and island chains that rise from the deepest parts of the ocean. These submarine volcanoes often remain active for millions of years, slowly building massive structures that eventually emerge above sea level to form volcanic islands. The Hawaiian island chain, the Aleutian Islands, and the islands of Japan all owe their existence to volcanic processes that begin in the deepest parts of the ocean. The chemical composition of seawater in the deepest places reflects billions of years of interaction between water and rock. As seawater circulates through the oceanic crust at subduction zones, it becomes enriched in various minerals and gases that are later released at hydrothermal vents and volcanic springs. This chemical cycling helps regulate the composition of the oceans and plays a crucial role in maintaining the conditions necessary for life on Earth. Recent advances in deep-sea exploration have revealed that the deepest places are far more dynamic and varied than previously thought. High-resolution mapping has revealed underwater rivers, waterfalls, and even lakes of dense, salty water that flows along the seafloor. These features create diverse habitats within the deep ocean, supporting different communities of organisms adapted to specific local conditions. The discovery of deep-sea coral reefs in some of the world's deepest places has challenged our understanding of where these ecosystems can thrive. Unlike their shallow water cousins, deep-sea corals do not depend on photosynthetic algae for energy, but instead filter nutrients directly from the water. These coral communities create complex three-dimensional habitats that support diverse assemblages of fish, crustaceans, and other organisms. The role of the deepest places in global ocean circulation cannot be overstated. The deep waters formed in polar regions sink to fill the deepest basins and trenches, creating a global conveyor belt of circulation that transports heat, nutrients, and dissolved gases around the world. This thermohaline circulation helps regulate Earth's climate and plays a crucial role in distributing the conditions necessary for life throughout the world's oceans. Climate change is beginning to affect even the deepest places on Earth. though the changes occur slowly and may take decades or centuries to fully manifest. As the oceans absorb excess carbon dioxide from the atmosphere, the deep waters gradually become more acidic, potentially affecting the organisms that have evolved to thrive in the stable conditions of the depths. Rising surface temperatures also affect the formation of deep water in polar regions, potentially altering the circulation patterns that have remained stable for thousands of years. The study of the deepest places provides insights not just into our own planet, but into the potential for life elsewhere in the universe. The extreme conditions found in oceanic trenches and deep caves are similar to those that might exist on other worlds, such as the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. Understanding how life adapts to these extreme conditions on Earth helps scientists develop strategies for searching for life in similar environments elsewhere in the solar system. The technological challenges of exploring the deepest places continue to drive innovation in materials science, robotics, and life support systems. The development of pressure-resistant electronics, advanced lighting systems, and autonomous underwater vehicles specifically for deep-sea exploration has applications far beyond oceanography. These technologies find uses in space exploration, medical devices, and industrial applications where extreme conditions must be endured. The deepest places on Earth serve as natural archives of our planet's history, preserving evidence of past climates, ocean conditions, and biological communities in their sediments and rock formations. Ice cores from polar regions provide detailed records of atmospheric conditions over the past few 100,000 years. But the sediments of the deep ocean extend this record back millions of years, offering insights into how Earth's climate system has evolved over geological time. The isolation of the deepest places has led to the evolution of endemic species found nowhere else on Earth. Many deep-sea organisms are so highly specialized for their extreme environment that they cannot survive anywhere else, making them particularly vulnerable to environmental changes. The study and conservation of these unique species is crucial for understanding the full extent of life's diversity on our planet. As our exploration of the deepest places continues, we are constantly reminded of how much we still don't know about our own planet. Each expedition reveals new species, new geological features, and new insights into how life can adapt to extreme conditions. The deepest places represent the final frontier of Earth exploration, vast regions that remain as mysterious and alien to us as the surface of distant planets. The deepest places exist in a realm of profound quietude, where the rhythms of life operate according to principles far removed from our surface experience. In these spaces, time moves differently, measured not in days and seasons, but in the slow accumulation of sediments, the gradual evolution of species, and the patient circulation of ancient waters. Here, in the gentle darkness of the deep, our planet reveals its most fundamental nature, a world of subtle processes and quiet persistence that has continued unchanged for millions of years. In these deepest places, we find not emptiness, but fullness, not absence, but presence of a different kind. The darkness here is not the darkness of void, but of peaceful completion, where light is not needed, because other senses, other ways of being, have evolved to take its place. The pressure that would crush surface dwellers becomes, for the creatures of the deep, simply the natural condition of existence, as normal and necessary as the air we breathe. These hidden depths remind us that most of our world exists beyond our daily awareness, in spaces of patient quiet, where the essential work of the planet continues without fanfare or recognition. In the deepest caves, where water has carved cathedral spaces in solid stone, and in the deepest trenches, where life thrives in conditions that seem impossible, we find expressions of Earth's creative power that inspire both humility and wonder. The deepest places teach us that mystery and beauty can coexist with scientific understanding, that knowing more about these extreme environments only deepens our appreciation for their remarkable nature. They exist as testament to the patience of geological processes, the adaptability of life, and the enduring mystery of our own planet, much of which remains peacefully hidden beneath the surface, waiting quietly in the gentle darkness below. The gentle currents that flow through these deepest places carry with them the memory of countless journeys across the ocean floor. These deep-sea streams move with purpose, but without haste, following pathways carved by density differences and the Earth's rotation, creating a circulation system so vast and slow that a single drop of water might take 1,000 years to complete its circuit from the deepest trenches back to the surface world above. Within this ancient circulation, dissolved minerals tell their own quiet stories. Iron and manganese, leached from volcanic rocks over millions of years, precipitate slowly onto the seafloor, creating nodules that grow at rates measured in millimeters per million years. These polymetallic nodules, scattered across the abyssal plains like dark pearls, represent one of the slowest geological processes on Earth, a patient accumulation of metals that continues undisturbed in the eternal darkness. The magnetic properties of rocks in the deepest places preserve a record of Earth's changing magnetic field, frozen in time as the minerals cooled and solidified on the ancient seafloor. These magnetic signatures create invisible stripes across the ocean floor, documenting the periodic reversals of Earth's magnetic poles that have occurred throughout geological history. Reading these magnetic patterns is like deciphering a vast library written in stone, each stripe telling the story of when and where it formed. The chemistry of the deep ocean differs subtly but significantly from that of surface waters. Carbon dioxide, absorbed from the atmosphere decades or centuries ago, has made the deep waters slightly more acidic and rich in dissolved carbonate minerals. This carbonate chemistry plays a crucial role in regulating Earth's climate, as the deep ocean acts as a vast reservoir for carbon, storing it away from the atmosphere for extended periods. Oxygen levels in the deepest places are lower than at the surface, but still sufficient to support life. This oxygen, dissolved into the water when it was last at the surface in polar regions, gradually decreases as it is consumed by deep-sea organisms during the water's long journey through the ocean basins. The distribution of oxygen in the deep ocean creates distinct zones where different types of organisms can thrive, each adapted to specific oxygen concentrations. The discovery that certain bacteria in the deepest trenches can survive entirely without oxygen has opened new chapters in our understanding of life's possibilities. These anaerobic organisms derive energy from chemical reactions involving sulfur, methane, and other compounds, creating ecosystems that operate on fundamentally different principles from those of the surface world. Their existence suggests that life might be possible in environments previously thought to be completely sterile. The sedimentary layers that accumulate in the deepest basins contain microscopic shells of foraminifera, single-celled organisms that lived in the surface waters millions of years ago. These tiny fossils, preserved in the deep-sea mud, record changes in ocean temperature and chemistry over geological time. By analyzing the isotopic composition of these ancient shells, scientists can reconstruct past climates with remarkable precision, revealing how Earth's climate system has responded to natural changes over millions of years. Deep-sea turbidity currents, underwater avalanches of sediment-laden water, occasionally disturb the usual tranquility of the deepest places. These powerful flows can travel for hundreds of kilometers across the ocean floor, carving submarine canyons and depositing thick layers of sediment in the deepest basins. Though infrequent, these events play important roles in shaping the topography of the deep sea floor and transporting organic matter from shallow waters to the deepest trenches. The pressure waves generated by distant earthquakes travel through the solid earth and emerge at the sea floor of the deepest trenches, creating subtle vibrations that can be detected by sensitive instruments These seismic waves carry information about the Earth's internal structure, allowing scientists to study the composition and properties of our planet's deep interior by monitoring their arrival times and characteristics at ocean floor seismometers. The interaction between seawater and hot volcanic rocks at mid-ocean ridges creates hydrothermal circulation systems that extend deep into the oceanic crust. Cold seawater seeps down through cracks in the seafloor, is heated by contact with hot rocks, and rises back to the surface carrying dissolved minerals and gases. This process, occurring over timescales of thousands of years, helps regulate the chemical composition of seawater and creates the conditions necessary for hydrothermal vent ecosystems. Some of the most remarkable discoveries in recent years have come from the study of subsurface life in the deepest ocean sediments. Microorganisms living within the seafloor itself, sometimes called the deep biosphere, may represent a significant fraction of all life on Earth. These organisms live in the spaces between sediment grains, deriving energy from chemical reactions and reproducing so slowly that individual generations might span centuries. The study of these subsurface microbes has revealed that life can exist under conditions previously thought impossible. Some organisms have been found living at temperatures approaching the boiling point of water, while others survive in environments with pH levels that would dissolve metal. These extremophiles, as they're known, expand our understanding of life's limits and provide insights into how life might exist in extreme environments elsewhere in the universe. The deepest places serve as natural laboratories for studying the effects of pressure on biological and chemical processes. Under the extreme pressures found in oceanic trenches, water itself becomes denser and less compressible, while chemical reactions proceed at different rates than they do at the surface. These pressure effects influence everything from the folding of proteins in living organisms to the dissolution of minerals in seawater. Recent technological advances have allowed scientists to collect samples from the deepest parts of the ocean and maintain them under high pressure during transport to surface laboratories. These pressure-maintaining systems have revealed that many deep-sea organisms die when brought to the surface, not because of temperature or chemical changes, but simply because their cellular structures collapse when the pressure is removed. The bioluminescence produced by deep-sea organisms represents one of the most energy-efficient forms of light production known to science. These biological light sources convert chemical energy into photons with remarkably little waste heat, creating cool, blue-green illuminations that can be seen for kilometers through the clear, deep water. The study of bioluminescence has led to advances in biotechnology, including the development of new types of biological sensors and imaging agents for medical research. The sounds produced by geological processes in the deepest places create a natural acoustic environment that has remained largely unchanged for millions of years. The slow creaking of tectonic plates, the distant rumble of underwater landslides, and the gentle hiss of gas bubbles rising from hydrothermal vents combine to create a symphony of earth sounds that few humans have ever heard. These natural sounds provide important information about geological processes and help scientists monitor changes in deep-sea environments. The formation of deep-sea mineral deposits occurs through processes so slow they're almost imperceptible on human timescales. Manganese nodules grow by accreting layers of metal-rich sediments at rates of millimeters per million years, while polymetallic sulfide deposits form around hydrothermal vents over thousands of years as hot. Mineral-rich water precipitates metals upon contact with cold seawater. These deposits represent some of the slowest manufacturing processes on Earth. The deep ocean's role as a repository for cosmic dust adds an extraterrestrial dimension to the sediments of the deepest places. Micrometeorites, tiny particles of cosmic debris that constantly rain down on Earth, accumulate slowly in deep-sea sediments, creating a record of our solar system's history. These cosmic particles, preserved in the quiet depths, provide scientists with samples of material from asteroids, comets, and even other planets that would otherwise be impossible to obtain. The study of how sound travels in the deep ocean has revealed the existence of natural sound channels that can carry whale songs and other acoustic signals across entire ocean basins. These deep sound channels, created by the specific temperature and pressure conditions in the deep ocean, act like underwater highways for acoustic communication, allowing marine animals to communicate over distances of thousands of kilometers. The pressure conditions in the deepest trenches create unique opportunities for studying matter under extreme conditions. Water under such pressure behaves differently than surface water, becoming denser and developing properties that don't exist under normal conditions. These extreme pressure environments serve as natural laboratories for physics research, providing insights into the behavior of matter under conditions similar to those found in the interiors of planets. The oldest water on Earth is found in the deepest parts of the ocean, where circulation patterns move so slowly that some water masses have been isolated from the surface for over 1,000 years. This ancient water carries with it the chemical signatures of past ocean conditions, preserving information about how the oceans have changed over historical time periods. The study of these old water masses helps scientists understand long-term trends in ocean chemistry and circulation. Deep sea glass sponge reefs, found in some of the deeper parts of the ocean, create complex three-dimensional structures that can persist for thousands of years. These silicate skeletons, built slowly by filter-feeding sponges, form underwater gardens of remarkable beauty and complexity. The sponges themselves can live for centuries, growing slowly in the nutrient-poor environment and creating habitat for numerous other deep-sea organisms. The relationship between the deepest places and global climate operates on timescales that span thousands of years. Changes in deep water formation in polar regions can affect the properties of deep water masses for centuries, slowly altering the conditions in the deepest trenches and abyssal basins. These long-term changes in deep ocean conditions play crucial roles in regulating Earth's climate system, but they occur so slowly that their effects are often invisible on human timescales. The discovery of active mud volcanoes in some of the deepest parts of the ocean has revealed another mechanism by which the Earth's interior communicates with the surface. These underwater mountains, built from sediments and fluids expelled from deep within the oceanic crust, create unique chemical environments that support specialized communities of organisms. The fluids emerging from mud volcanoes often contain gases and minerals that provide insights into the composition and processes occurring deep within the Earth. Some of the most pristine environments on Earth are found in the deepest places, where human influence has been minimal until very recently. These environments serve as reference sites for understanding how Earth systems functioned before human industrial activity began to alter global climate and ocean chemistry. The study of these pristine deep-sea environments provides crucial baselines for assessing the magnitude and rate of human-induced environmental changes. The role of the deepest places in the global carbon cycle extends beyond simple storage of carbon dioxide. Deep-sea organisms play active roles in processing and transforming carbon compounds, while geological processes in subduction zones return some carbon to the atmosphere through volcanic activity. This deep carbon cycle operates on timescales of millions of years, helping to regulate Earth's long-term climate stability. Recent discoveries of deep-sea rivers and waterfalls have revealed that the seafloor topography is much more dynamic than previously thought. These underwater rivers, formed by dense, salty water flowing along the seafloor, can extend for hundreds of kilometers and create their own ecosystems along their banks. The waterfalls, where dense water cascades over underwater cliffs, generate turbulence and mixing that affects the distribution of nutrients and organisms in the deep sea. The magnetic field generated by Earth's core creates subtle effects in the deepest parts of the ocean, influencing the behavior of magnetic particles in the water and sediments. Some deep-sea organisms are thought to use these magnetic fields for navigation, following magnetic contours across the seafloor much as surface animals might follow topographical features. The study of biological magnetism in the deep sea is revealing new ways that life can sense and respond to environmental cues. The deepest places serve as natural archives of Earth's impact history, preserving in their sediments the signatures of asteroid and comet impacts that occurred millions of years ago. These impact signatures, including unusual concentrations of rare metals and shocked minerals, provide evidence for catastrophic events that shaped the evolution of life on Earth. The quiet accumulation of sediments in the deepest basins has preserved this record of cosmic catastrophes with remarkable fidelity. The study of deep-sea ecosystems has revealed the importance of chemical gradients in structuring biological communities. Small differences in temperature, oxygen concentration, or chemical composition can create distinct microenvironments within the same general area, each supporting different assemblages of organisms. These chemical gradients, often invisible to surface-dwelling humans, create a complex mosaic of habitats in the seemingly uniform environment of the deep sea. The pressure-adapted enzymes found in deep-sea organisms represent millions of years of evolutionary experimentation with protein folding and stability. These biological molecules, which maintain their function under pressures that would destroy conventional proteins, have inspired the development of new biotechnological applications. Industrial processes that require high pressure, such as certain chemical syntheses and food processing techniques, benefit from insights gained from studying these natural pressure-adapted systems. The acoustic properties of the deepest places create unique sound environments that affect how marine animals communicate and navigate. The absorption of certain sound frequencies by the dense, high-pressure water means that deep-sea animals must use specific frequency ranges for effective communication. This has led to the evolution of specialized sound-producing and sound-detecting organs in many deep-sea species, creating an acoustic ecology quite different from that of surface waters. The symbiotic relationships between deep-sea organisms and their associated microbes represent some of the most intimate partnerships in the natural world. Tube worms at hydrothermal vents house billions of bacteria within their tissues, providing them with a protected environment in exchange for nutrients produced by bacterial chemosynthesis. These relationships are so tightly integrated that the host organisms have lost many basic functions, relying entirely on their bacterial partners for essential nutrients. The deepest places play crucial roles in the global phosphorus cycle, one of the key nutrient cycles that sustains life on Earth. Phosphorus-bearing minerals weather slowly in the deep ocean, while organic matter settling from surface waters carries phosphorus into the deep sea sediments. The balance between these inputs and outputs, operating over geological timescales, helps regulate the availability of this essential nutrient for marine ecosystems worldwide. Deep-sea chemosynthetic ecosystems represent alternative evolutionary pathways that life has taken in the absence of sunlight. These communities, based on bacterial conversion of chemical energy rather than solar energy, demonstrate that complex ecosystems can exist independently of photosynthesis. The discovery of these chemosynthetic communities has expanded our understanding of where life might exist, both on Earth and potentially on other worlds, with similar chemical energy sources. The study of how organic matter is preserved in deep-sea sediments has provided insights into the conditions necessary for fossil formation. The cold, low-oxygen environment of the deep sea can preserve organic molecules for millions of years, creating a record of past life that extends far back in Earth's history. These molecular fossils, called biomarkers, provide information about ancient organisms and environments that left no conventional fossil record. The deepest places are connected to the surface world through the migration patterns of certain marine animals. Some deep sea fish undertake vertical migrations that span thousands of meters, traveling from the depths to surface waters to feed and then returning to the deep. These migrations create biological connections between the surface and deep-sea ecosystems, transferring energy and nutrients between environments that are otherwise largely separate. The formation of deep-sea sedimentary structures, such as ripples and dunes, occurs through the action of deep water currents that move at speeds of only centimeters per second. Despite their gentle flow, these currents can transport fine sediments over great distances, creating patterns on the seafloor that mirror those found in terrestrial deserts. The study of these deep-sea sedimentary structures provides insights into the dynamics of deep water circulation and the long-term evolution of seafloor topography. Recent advances in deep-sea robotics have enabled scientists to conduct long-term monitoring studies in the deepest places, revealing that these environments are more dynamic than previously thought. Seasonal changes in the delivery of organic matter from surface waters create subtle but detectable variations in deep-sea communities, while longer-term climate cycles affect the properties of deep water masses and the organisms they support. The role of deep-sea trenches as sediment traps has important implications for understanding global geochemical cycles. These deepest places accumulate sediments and associated chemicals at rates much higher than the surrounding abyssal plains, creating concentrated repositories of elements that are important for climate regulation and ecosystem function. The study of sediment accumulation in trenches provides insights into how materials are transported and stored in the deep ocean. The discovery of deep-sea lakes, bodies of dense, salty water that pool in seafloor depressions, has revealed another type of extreme environment within the deepest places. These underwater lakes, with their distinct chemical compositions and sharp boundaries with the surrounding seawater, support unique microbial communities and create unusual habitats for deep-sea organisms. The study of these environments provides analogues for understanding similar features that might exist on other worlds. The deepest places serve as natural laboratories for studying the limits of life under extreme conditions of pressure, temperature, and chemical stress. The organisms found in these environments push the boundaries of what we consider possible for life, surviving under conditions that would be instantly lethal to most surface-dwelling species. These studies have important implications for astrobiology and the search for life in extreme environments elsewhere in the universe. The slow rate of change in the deepest places creates environments where evolutionary processes operate differently than in more dynamic surface habitats. The stability of deep-sea conditions over geological timescales has allowed some lineages to persist with relatively little change for millions of years, creating what scientists call living fossils that provide insights into ancient life forms and evolutionary processes. The chemical weathering of rocks in the deepest parts of the ocean occurs at rates so slow they're measured in geological time. Basaltic rocks of the oceanic crust react with seawater over millions of years, gradually releasing minerals that affect ocean chemistry and providing nutrients for deep-sea ecosystems. This weathering process, though imperceptibly slow, plays important roles in regulating the chemical composition of seawater and the global climate system. The deepest places are repositories for some of the oldest materials on Earth's surface. Sediments in the deepest ocean basins contain minerals and organic compounds that have remained virtually unchanged for millions of years, preserved by the stable conditions and slow sedimentation rates. These ancient materials provide direct links to Earth's past, offering glimpses into environmental conditions and biological processes from previous geological eras. The study of how pressure affects the behavior of gases in the deep ocean has revealed unique chemical environments in the deepest places. Gases that would form bubbles at the surface remain dissolved in solution under the extreme pressures of the deep trenches, creating chemical conditions that don't exist anywhere else on Earth. These high-pressure gas solutions support unusual types of chemical reactions and may provide energy sources for specialized deep-sea organisms. The role of the deepest places in global ocean mixing operates through processes so subtle they're almost imperceptible. Small differences in water density created by variations in temperature and salinity, drive circulation patterns that can take centuries to complete their cycles. This deep mixing helps distribute heat, nutrients, and dissolved gases throughout the world's oceans, playing crucial roles in regulating Earth's climate and supporting marine ecosystems worldwide. Deep-sea mineral formations, including natural glass structures created by the rapid cooling of volcanic materials, create unique habitats in the deepest places. These glass formations, with their complex three-dimensional structures and unusual surface properties, provide attachment sites for filter-feeding organisms and create microenvironments with distinct chemical and physical characteristics. The study of these formations provides insights into both geological processes and the ecology of deep-sea communities. The deepest places preserve evidence of Earth's magnetic field reversals in the magnetic properties of their sediments and rocks. These magnetic reversals, which occur irregularly over geological time, are recorded in the seafloor like a vast magnetic tape recorder. The study of these magnetic records from the deepest parts of the ocean has provided crucial evidence for understanding how Earth's magnetic field behaves and changes over time. The interaction between deep-sea organisms and their chemical environment creates feedback loops that can influence the chemistry of the deep ocean over long time periods. The metabolic activities of deep-sea bacteria, for example, can affect the concentration of dissolved gases and nutrients in ways that influence the broader deep-sea ecosystem. These biological feedbacks operate slowly but can have significant cumulative effects over geological timescales. The deepest places serve as refugia for ancient lineages of organisms that have survived multiple mass extinction events. The stability of deep-sea environments has provided safe havens for species that disappeared from other parts of the ocean, creating communities that preserve evolutionary relationships dating back hundreds of millions of years. The study of these relict communities provides insights into how life responds to global environmental changes. Some of the most complex chemical processes on Earth occur in the deepest places, where the interaction between seawater, rock, and living organisms creates chemical environments of remarkable complexity. Multiple chemical reactions proceed simultaneously at different rates, creating chemical gradients and microenvironments that support specialized communities of organisms. Understanding these chemical processes requires interdisciplinary approaches that combine geology, chemistry, and biology. The deepest places are connected to global climate through their role in the thermohaline circulation, the global conveyor belt of ocean currents driven by differences in water density. Changes in surface conditions in polar regions can affect the properties of deep water masses, which then carry these changes to the deepest parts of the ocean over periods of decades to centuries. This connection means that the deepest places are ultimately linked to climate processes occurring at Earth's surface. The study of deep-sea ecosystems has revealed the importance of rare elements and trace compounds in supporting life under extreme conditions. Organisms in the deepest places often concentrate rare metals and unusual chemical compounds that play crucial roles in their metabolism and survival. Understanding how these organisms acquire and use rare elements provides insights into both deep-sea ecology and the biogeochemical cycles that regulate the availability of these materials. The deepest places represent the ultimate expression of Earth's creative geological forces, where the slow but relentless processes of plate tectonics, sedimentation, and chemical weathering have created environments unlike anywhere else in the solar system. These places exist as testament to the power of gradual change, demonstrating how imperceptible processes operating over vast timescales can create features of extraordinary depth and complexity. In these deepest places, we find not chaos, but order, not emptiness, but richness beyond measure. The darkness here is not absence, but completion, a state where other forms of energy and interaction take precedence over the light-dependent processes that dominate our surface world. The pressure that seems so extreme to us is simply the natural condition for the organisms that call these depths home. As normal and necessary as the atmospheric pressure we experience without thought, the profound quiet of these deepest places speaks not of lifelessness, but of different rhythms, slower cycles, patient processes that unfold according to timescales that dwarf human experience. Here, in the gentle darkness, surrounded by the weight of kilometers of water or solid rock, our planet continues its ancient work of creating and sustaining life in forms so specialized and beautiful, they seem to belong to dreams rather than reality. These hidden depths remind us that most of our world exists beyond our immediate awareness, in spaces of peaceful completeness, where the essential processes of Earth continue their quiet work. The deepest places are not alien worlds, but integral parts of our planetary system, connected through invisible threads of circulation and chemistry to every drop of rain that falls, every breath of wind that blows, every living thing that grows in the sunlight above. In contemplating these deepest places, we are reminded of the vast scales on which our planet operates, the patient accumulation of small changes that create profound results, and the remarkable ability of life to find ways to thrive even in the most extreme conditions imaginable. They exist as gentle reminders that mystery and wonder are not diminished by scientific understanding, but enhanced by it, that knowing how these places formed and function only deepens our appreciation for their quiet majesty. The deepest places teach us patience, showing us worlds where time moves according to different rules, where the urgent concerns of surface life give way to slower rhythms, deeper currents, more fundamental processes. In their peaceful darkness, we find not something to fear, but something to admire, spaces where Earth reveals its most essential nature, creative and sustaining, patient and enduring, quietly magnificent in ways that invite contemplation rather than conquest. As we rest in the knowledge of these deepest places, we can find comfort in their persistence, their quiet stability, their role as keepers of Earth's memory, and guardians of its most ancient processes. They exist not as empty spaces, but as full expressions of our planet's complexity, reminders that beneath the familiar surface of our daily world lies a realm of gentle mystery, patient depth, and enduring wonder that continues its quiet work in the peaceful darkness below. The microscopic world that thrives in these deepest places operates according to principles that seem almost magical in their elegance. Bacteria living in the sediments thousands of meters below the seafloor reproduce so slowly that a single generation might span decades or even centuries. Their cellular machinery has been fine-tuned over millions of years to function efficiently in environments where energy is scarce and every chemical reaction must be carefully managed. These ancient microbes have developed ways of storing energy that allow them to survive periods of dormancy lasting thousands of years. When conditions are favorable, they can resume their metabolic activities as if no time has passed at all. Some researchers believe that certain bacteria in the deepest ocean sediments might be among the oldest living organisms on Earth, individual cells that have persisted unchanged since before human civilization began. The chemistry of life in these deepest places relies on elements and compounds that are rare or absent in surface environments. Selenium, molybdenum, and other trace metals play crucial roles in the enzymes that allow deep-sea organisms to process energy and maintain their cellular functions. These elements, concentrated by geological processes over millions of years, create chemical environments that support forms of life unknown in the sunlit world above. The study of these deep-sea chemical processes has revealed new pathways by which life can extract energy from its environment. Some deep-sea bacteria can use the energy stored in chemical bonds between sulfur atoms, while others derive energy from the radioactive decay of uranium and other elements naturally present in seafloor sediments. These alternative energy sources demonstrate that life is far more adaptable and creative than we once imagined. The pressure-induced changes in water structure at great depths create unique physical environments that affect how molecules interact and how chemical reactions proceed. Under extreme pressure, water molecules pack more tightly together, creating a denser medium that can dissolve different types of minerals and support different types of chemical processes. These pressure-modified environments exist nowhere else on Earth, creating natural laboratories for studying matter under extreme conditions. The acoustic environment of the deepest places is shaped by the unique properties of water under extreme pressure. Sound waves travel differently through this dense medium, creating natural sound channels that can carry certain frequencies for vast distances while absorbing others completely. The result is an acoustic landscape where the calls of distant whales might be heard clearly while nearby sounds disappear entirely into the absorbing depths. Some of the most remarkable discoveries in the deepest places have come from studying how life adapts to the complete absence of circadian rhythms. In environments where no sunlight has ever penetrated, organisms must find other ways to regulate their biological processes and coordinate their activities. Many deep-sea creatures have evolved internal clocks based on chemical cycles or the slow rhythms of deep ocean currents rather than the daily cycle of light and darkness. The geological processes that maintain the deepest places operate with a patience that dwarfs human comprehension. The slow recycling of oceanic crust through subduction zones takes millions of years to complete a single cycle. Yet this process has continued uninterrupted for billions of years, gradually shaping and reshaping the sea floor. Each grain of sediment that settles into a deep sea trench represents the end of a journey that might have begun as a mountain peak millions of years ago. The magnetic minerals in deep sea sediments preserve not only records of Earth's magnetic field reversals, but also evidence of the planet's interaction with cosmic forces. Solar wind particles, trapped in Earth's magnetic field and eventually deposited in marine sediments, create subtle chemical signatures that tell the story of our planet's relationship with the Sun over geological time. These cosmic influences, recorded in the quiet depths, connect the deepest places to the broader universe beyond our planet. The formation of deep-sea mineral deposits represents some of the slowest manufacturing processes in the natural world. Ferromanganese crusts, which coat rock surfaces in the deep ocean, grow at rates so slow that a layer the thickness of a human hair might take 1,000,000 years to form. Yet these crusts can reach thicknesses of several centimeters, representing continuous growth over tens of millions of years in the stable environment of the deep sea. The symbiotic relationships that have evolved in the deepest places demonstrate life's remarkable ability to form partnerships that benefit all participants. Clams living around hydrothermal vents house bacteria in specialized organs, providing them with a protected environment while receiving nutrients produced by bacterial chemosynthesis. These partnerships are so intimate that the host organisms have lost the ability to digest food in the conventional sense, relying entirely on their bacterial partners for sustenance. The study of how proteins fold and function under extreme pressure has revealed fundamental principles about the relationship between molecular structure and biological activity. The proteins found in deep-sea organisms maintain their function under pressures that would unfold and destroy surface proteins. Yet they accomplish this through subtle changes in amino acid sequence that preserve the essential features of protein structure while adapting to extreme conditions. The role of the deepest places in regulating Earth's climate extends beyond their function as carbon reservoirs. The slow circulation of deep water helps distribute heat around the globe, moderating temperature differences between different regions and stabilizing climate patterns over long time periods. Changes in deep water circulation, though they occur slowly, can have profound effects on global climate that persist for centuries or millennia. The discovery of natural glass formations in the deepest parts of the ocean has revealed another way that geological processes create unique habitats for life. These glass structures, formed when volcanic material cools rapidly in contact with cold seawater, create surfaces with unusual chemical and physical properties that support specialized communities of microorganisms. The study of life on these glass surfaces provides insights into how organisms colonize and adapt to new types of substrates. Deep-sea hydrothermal vents create temporary oases of warmth and chemical activity in the otherwise cold and stable deep ocean environment. The life cycles of these vents, from their initial formation to their eventual extinction, create dynamic habitats that support different communities at different stages. Young vents with high-temperature, mineral-rich fluids support one type of community, while older, cooler vents support different assemblages of organisms adapted to the changing chemical conditions. The pressure gradients that exist within the deepest places create microenvironments with different physical and chemical properties over relatively short distances. A difference in depth of just a few meters can create significant differences in pressure that affect which organisms can survive and how chemical reactions proceed. These pressure gradients create complex three-dimensional habitats that support diverse communities within what might appear to be uniform deep-sea environments. The study of how gases behave under the extreme pressures of the deepest places has revealed unique states of matter that don't exist under normal conditions. Carbon dioxide, which forms bubbles at atmospheric pressure, remains dissolved in seawater at great depths, creating carbonic acid solutions that affect the pH and chemical reactivity of deep-sea environments. These pressure-induced changes in gas behavior create chemical conditions that support unusual types of metabolic processes. The ancient age of some deep-sea environments has allowed evolutionary processes to operate over timescales rarely seen in other habitats. Some deep-sea lineages have remained virtually unchanged for tens of millions of years, preserved by the stability of their environment and the lack of major disturbances. These living fossils provide direct links to ancient Earth, offering glimpses into how life functioned in past geological eras. The role of deep-sea currents in shaping the topography of the deepest places operates through processes so gentle they seem almost imperceptible. Currents moving at speeds of mere centimeters per second can, over geological time, carve channels and valleys in the seafloor, transport sediments across ocean basins, and create the subtle topographical features that provide habitat diversity in the deep sea. These currents follow predictable patterns based on water density and the Earth's rotation, creating a slowly moving network of underwater rivers that connect the deepest places to the broader ocean system. The chemical weathering processes that occur in the deepest places proceed at rates so slow they challenge our understanding of how chemical reactions can continue over such extended time periods. The reaction between seawater and basaltic rocks of the oceanic crust, for example, can continue for millions of years, gradually altering both the composition of the rock and the chemistry of the surrounding seawater. These ultra-slow reactions play important roles in regulating ocean chemistry and providing nutrients for deep-sea ecosystems. The preservation of organic molecules in deep-sea sediments creates natural archives that extend our knowledge of past life far beyond what is possible from conventional fossils. Lipids, proteins, and other biological molecules can survive for millions of years in the cold, low-oxygen environment of the deep sea, providing direct chemical evidence of ancient organisms and their metabolic processes. These molecular fossils reveal details about past ecosystems that would otherwise be lost to time. The magnetic properties of deep-sea basalts record not only the orientation of Earth's magnetic field when they formed, but also its intensity and the rate at which it was changing. This magnetic record, preserved in the rocks of the deepest ocean floor, provides a detailed history of how Earth's magnetic field has behaved over millions of years. The study of these magnetic records has revealed that Earth's magnetic field has undergone periods of rapid change and relative stability, with implications for understanding how the magnetic field affects life on Earth. The discovery of chemosynthetic bacteria living within the rocks of the oceanic crust has revealed an entirely new biosphere that exists independently of the surface world. These subsurface communities derive their energy from chemical reactions between rock and water, creating ecosystems that could potentially exist on other worlds with similar geological conditions. The biomass contained in these subsurface environments may rival that of all surface ecosystems combined, representing a hidden world of life that was unknown until recent decades. The study of how sound propagates through the complex topography of the deepest places has revealed that these environments have their own unique acoustic signatures. The interaction between sound waves and the irregular surfaces of the seafloor creates acoustic shadows and amplification zones that affect how marine animals communicate and navigate. Some deep-sea organisms have evolved to exploit these acoustic properties, using the topography of the seafloor to enhance their calls, or to hide from predators in acoustic shadows. The role of the deepest places as repositories for cosmic debris adds an extraterrestrial dimension to their geological significance. Cosmic dust, micrometeorites, and the occasional larger meteorite fragment accumulate slowly in deep-sea sediments, creating a record of our solar system's history that spans millions of years. The study of this cosmic material provides insights into the composition and evolution of our solar system that would be impossible to obtain from terrestrial rocks. The formation of natural underwater springs in the deepest places creates unique chemical environments where fresh water, heated and mineralized by its passage through the oceanic crust, emerges into the salt water of the deep sea. These springs create chemical gradients and mixing zones that support specialized communities of organisms adapted to the changing salinity and chemical composition. The study of these environments provides analogues for understanding similar features that might exist on other worlds with subsurface oceans. The slow but continuous process of sediment burial in the deepest places creates pressure and temperature conditions that gradually transform organic matter into new chemical compounds. This natural process of chemical transformation, operating over millions of years, creates deposits of organic compounds that preserve information about past ecosystems, or providing energy sources for subsurface microbial communities. The study of these processes helps scientists understand how organic matter is preserved and transformed over geological time. The interaction between tidal forces and the topography of the deepest places creates subtle but persistent currents that affect the distribution of organisms and the transport of nutrients. Even in the deepest trenches, thousands of meters below the surface, the gravitational pull of the moon and sun creates tidal currents that follow predictable patterns. These deep-sea tides are much weaker than surface tides, but they operate continuously, creating a gentle stirring that prevents complete stagnation and helps maintain the chemical gradients that support deep-sea life. The study of how ice crystals form under the extreme pressures of the deepest places has revealed new phases of water that exist only under these conditions. At the pressures found in the deepest ocean trenches, water can form crystalline structures that are denser than normal ice, creating unusual physical environments that affect how other molecules behave. These high-pressure ice phases may play important roles in the chemistry of deep-sea environments and could exist in the subsurface oceans of icy moons elsewhere in the solar system. The discovery of natural fiber optic systems in some deep-sea organisms has revealed how life can adapt to create and manipulate light in environments of total darkness. Certain deep-sea sponges contain silica spicules that act as biological optical fibers, channeling bioluminescent light with remarkable efficiency. These biological light guides demonstrate principles of optics that have inspired advances in fiber optic technology and reveal the sophisticated ways that life can manipulate physical properties to survive in extreme environments. The role of deep-sea trenches as natural laboratories for studying the effects of extreme pressure on chemical reactions has provided insights that extend far beyond marine science. The unique chemical conditions found in these environments have revealed new reaction pathways and molecular structures that have applications in materials, science, pharmaceutical research, and industrial chemistry. The study of pressure-adapted enzymes from deep-sea organisms has led to the development of new biotechnological applications that require high-pressure conditions. The formation of deep-sea brine pools, underwater lakes of dense, salty water that collect in seafloor depressions, creates some of the most unusual environments in the deepest places. These brine pools have sharp boundaries with the surrounding seawater, creating underwater lakes complete with their own shorelines and unique chemical properties. The organisms that live around these brine pools must adapt to extreme changes in salinity and chemical composition, leading to the evolution of highly specialized biological communities. The study of how organic compounds are synthesized under the extreme conditions of the deepest places has revealed alternative pathways for the formation of complex molecules that are essential for life. Some of the chemical reactions that occur around hydrothermal vents can produce amino acids, lipids, and other organic compounds from simple inorganic precursors, demonstrating that the building blocks of life can form spontaneously under certain geological conditions. These discoveries have important implications for understanding how life might have originated on Earth and could potentially exist elsewhere in the universe. The magnetic navigation systems used by some deep-sea organisms rely on the subtle variations in Earth's magnetic field that are preserved in the rocks of the sea floor. These organisms can detect and follow magnetic contours across the ocean floor, using the planet's magnetic field as a natural GPS system that allows them to navigate across vast distances in the darkness of the deep sea. The study of biological magnetism in these environments is revealing new ways that life can sense and respond to physical forces that are invisible to human senses. The process of fossilization in deep-sea environments occurs under conditions that can preserve biological structures with extraordinary fidelity. The cold temperatures, high pressure, and low oxygen conditions of the deep sea create ideal conditions for the preservation of soft tissues and delicate structures that would normally decompose rapidly. Some deep-sea fossils retain cellular details that provide unprecedented insights into the anatomy and physiology of ancient organisms. The chemical communication systems used by deep-sea organisms operate in an environment where chemical signals can persist for extended periods due to the stable conditions and slow water movement. Pheromones and other chemical signals released by deep-sea organisms can create chemical trails that last for hours or days, allowing for complex forms of communication and coordination that are impossible in more turbulent surface environments. These chemical communication systems demonstrate how life adapts its behavior to the unique properties of extreme environments. The role of the deepest places in the global water cycle extends beyond their function as endpoints for surface water circulation. The chemical and isotopic composition of water in the deepest parts of the ocean reflects its long journey through the global circulation system, carrying with it the signatures of evaporation, precipitation, and mixing processes that occurred decades or centuries ago. The study of these water masses provides insights into how the global water cycle has changed over time and how it might respond to future climate changes. The formation of natural semiconducting materials in deep-sea environments has revealed how geological processes can create substances with unusual electrical properties. Certain minerals that form around hydrothermal vents have semiconducting properties that could potentially support electronic processes in biological systems. The discovery of these materials has opened new areas of research into the possible role of semiconducting minerals in the origin and evolution of life. The study of how sound absorption varies with depth in the deepest places has revealed that these environments have unique acoustic properties that affect how marine animals use sound for communication and echolocation. The high pressure and density of deep water can absorb certain frequencies while allowing others to propagate over long distances, creating natural acoustic channels that deep-sea organisms have evolved to exploit. These acoustic properties make the deepest places fundamentally different from surface environments in terms of how information can be transmitted through sound. The discovery of natural superconducting materials in some deep-sea mineral deposits has revealed another way that extreme conditions can create unusual physical properties. Under the specific conditions of temperature, pressure, and chemical composition found in certain deep-sea environments, some materials can conduct electricity with zero resistance, a property that has important applications in technology and provides insights into how extreme conditions can alter the fundamental properties of matter. The role of deep-sea sediments as natural archives of atmospheric composition extends back millions of years, providing records of how Earth's atmosphere has changed over geological time. Dust particles, pollen grains, and other atmospheric debris that settle into the deepest ocean basins create layers that preserve information about past climates, volcanic eruptions, and even meteor impacts. These sedimentary archives provide crucial data for understanding long-term climate change and the factors that influence Earth's atmospheric composition. The study of how organisms in the deepest places maintain their cellular membranes under extreme pressure has revealed new insights into the fundamental properties of biological membranes. The lipids that make up cell membranes in deep-sea organisms have unique structures that remain flexible and functional under pressures that would solidify conventional membrane lipids. These pressure-adapted lipids have potential applications in biotechnology and provide insights into how life might function under extreme conditions on other worlds. The chemical gradients that exist within deep-sea hydrothermal vent systems create microenvironments with vastly different properties over distances of just centimeters. Temperature, pH, and chemical composition can change dramatically within the space of a few centimeters around a vent, creating a complex mosaic of chemical environments that support different types of organisms. The study of these chemical gradients provides insights into how life adapts to rapidly changing environmental conditions. The formation of natural crystal structures in the deepest places occurs under conditions that can create minerals with unusual properties and compositions. The combination of high pressure, specific chemical conditions, and long time periods allows for the growth of crystals with perfect atomic arrangements and unique optical, electrical, and mechanical properties. These natural crystals provide insights into how materials behave under extreme conditions and have potential applications in technology and industry. The study of how gas hydrates form and persist in the deepest places has revealed the existence of vast reservoirs of methane and other gases trapped in ice-like structures within deep-sea sediments. These gas hydrates represent one of the largest reservoirs of carbon on Earth, stored in solid form under the specific conditions of high pressure and low temperature found in the deep sea. The study of these gas hydrates has important implications for understanding climate change and energy resources. The role of deep-sea organisms as ecosystem engineers extends to their ability to modify the chemical and physical properties of their environment in ways that create habitat for other organisms. Tube worms that build large carbonate structures around hydrothermal vents create three-dimensional habitats that support diverse communities of smaller organisms. These biological constructions can persist for decades or centuries, creating stable habitat islands in the otherwise sparse deep-sea environment. The discovery of natural quantum effects in some deep-sea biological systems has revealed that quantum mechanics may play important roles in biological processes under extreme conditions. Certain enzymes found in deep-sea organisms appear to use quantum tunneling effects to catalyze chemical reactions that would be impossible under classical physics. These quantum biological effects demonstrate that life can exploit fundamental physical principles in ways that were previously thought to be limited to non-living systems. The study of how time perception might work in organisms living in the deepest places, where there are no daily cycles of light and darkness, has revealed alternative ways that biological systems can keep track of time. Some deep-sea organisms appear to use chemical oscillations or metabolic cycles as internal clocks, creating biological rhythms that are independent of external cues. These alternative timing systems demonstrate the flexibility of biological systems in adapting to environments that lack the temporal cues that most life depends on. The formation of natural metamaterials in deep-sea environments has revealed how extreme conditions can create substances with properties that seem to defy conventional physics. Certain biological and mineral structures found in the deepest places can manipulate light, sound, and other forms of energy in ways that have inspired advances in materials, science, and engineering. These natural metamaterials demonstrate principles that are being applied to develop new technologies with unusual and useful properties. The role of the deepest places as natural laboratories for studying the behavior of matter under extreme conditions continues to yield discoveries that advance our understanding of fundamental physics and chemistry. The unique combinations of pressure, temperature, and chemical composition found in these environments create conditions that cannot be replicated in conventional laboratories, making the deepest places invaluable resources for scientific research. The study of how information can be stored and transmitted in deep-sea environments has revealed that these systems have their own forms of memory and communication that operate on geological timescales. Chemical gradients in sediments can preserve information about past environmental conditions for millions of years, while the slow circulation of deep water can transport chemical signals across entire ocean basins over periods of centuries. These natural information storage and transmission systems demonstrate principles that could have applications in technology and help us understand how complex systems can maintain and transmit information over very long time periods. The deepest places serve as reminders that our planet operates according to principles and timescales that extend far beyond human experience. In these hidden depths, processes continue that began billions of years ago and will continue long after human civilization has ended. The patience of geological time, the persistence of slow chemical reactions, and the endurance of life under extreme conditions all speak to the remarkable stability and resilience of natural systems. The gentle circulation of ancient waters through the deepest trenches connects these remote places to every raindrop that has ever fallen, every breath of wind that has ever blown across the ocean's surface. The carbon atoms cycling through deep-sea ecosystems have been part of countless other life forms, from ancient plankton to modern whales, demonstrating the fundamental interconnectedness of all life on Earth. In the profound quiet of these deepest places, where the weight of water creates a silence so complete it seems to have substance, we find not emptiness, but fullness beyond measure. The darkness here is not the absence of light, but the presence of possibilities we are only beginning to understand. The pressure that seems so extreme to surface dwellers is simply the natural condition for forms of life so perfectly adapted to their environment that they represent millions of years of evolutionary refinement. These hidden depths teach us that mystery and understanding can coexist, that the more we learn about the deepest places, the more we appreciate their quiet majesty. They remind us that most of our world exists in peaceful darkness, in spaces where time moves according to different rhythms, where life follows patterns older than continents, where the essential work of the planet continues in forms so beautiful and strange they seem to belong to dreams. The deepest places exist not as voids to be filled or obstacles to be conquered, but as complete ecosystems, finished expressions of our planet's creative power. In their eternal darkness, surrounded by pressures that would crush surface structures, life not only survives but flourishes in forms that demonstrate the remarkable adaptability and resilience of living systems. As we rest in the knowledge of these deepest places, we can find comfort in their persistence, their role as keepers of Earth's memory, their function as guardians of processes that have continued unchanged for millions of years. They exist as gentle reminders that beneath the familiar surface of our daily world lies a realm of quiet completion, where the planet's most fundamental work continues in forms both ancient and eternal. In contemplating these depths, we are invited to appreciate the vast scales on which our Earth operates, the patient accumulation of small changes that create profound results over geological time. The deepest places teach us about persistence, about the value of slow processes, about the beauty that can exist in spaces removed from the urgency and brightness of surface life. They remind us that darkness and depth need not be feared, but can instead be appreciated as natural states of completion and rest. In the gentle darkness of the deepest places, our planet continues its ancient work of creating and sustaining life, hosting processes, and supporting communities that have found their perfect expression in the peaceful depths below. Here, in the quiet chambers of Earth's deepest reaches, we find not alien worlds, but integral parts of our planetary home, spaces where life has discovered ways to thrive that speak to the fundamental creativity and persistence of natural systems. These deepest places exist as sanctuaries of stability in a changing world, repositories of ancient wisdom, and expressions of life's remarkable ability to find beauty and meaning in the most unexpected conditions. In their profound quiet, surrounded by the gentle weight of water or stone, they offer us a different perspective on time, on change, on the nature of existence itself. They invite us to appreciate the value of slow processes, deep currents, and the patient work that continues unseen in the peaceful darkness below. The study of how life maintains its essential functions in these deepest places reveals biological innovations that seem almost beyond imagination. Proteins that would normally unfold and lose their function under such extreme pressure have evolved specialized structures that remain stable and active. These pressure-adapted molecules represent millions of years of evolutionary refinement, each amino acid carefully positioned to create structures that can withstand forces equivalent to having dozens of elephants standing on a postage stamp. The cellular membranes of deep-sea organisms contain unique lipid compositions that remain flexible and functional under conditions that would solidify conventional cell walls. These specialized fats, with their carefully arranged molecular structures, allow life to persist in environments where the pressure would otherwise crush cellular functions entirely. The study of these biological membranes has opened new understanding about the fundamental properties of life under extreme conditions. Within the deepest ocean trenches, the water itself takes on properties that differ significantly from surface seawater. The extreme pressure compresses water molecules more tightly together, creating a denser medium that affects how sound travels, how light behaves, and how chemical reactions proceed. This compressed water creates an environment so different from surface conditions that it represents almost another state of matter entirely. The acoustic landscape of these deepest places follows rules that seem to belong to an alien world. Certain sound frequencies can travel for thousands of kilometers through the dense, high-pressure water, while others are absorbed within meters of their source. Deep-sea creatures have evolved to exploit these acoustic properties, using specific frequency ranges that can penetrate the crushing depths, while avoiding frequencies that would simply disappear into the absorbing water. The study of bioluminescence in the deepest places has revealed some of the most efficient light-producing systems known to science. These biological light sources convert chemical energy directly into photons with remarkably little waste heat, creating cool, ethereal glows that can be seen for kilometers through the clear, deep water. The colors produced, primarily blues and greens, are specifically chosen by evolution because they travel furthest through the dense medium of the deep sea. Some deep-sea organisms have evolved light-producing organs so sophisticated they rival human engineering in their complexity and efficiency. Specialized cells containing luciferin and luciferase create controlled chemical reactions that produce light on demand. These biological light systems can be turned on and off instantly, dimmed or brightened as needed, and even modulated to create complex patterns of communication in the eternal darkness. The pressure at the bottom of the deepest trenches affects not just living organisms, but the very rocks and sediments of the seafloor. Under such extreme conditions, minerals can undergo phase transitions, changing their crystal structure and properties in ways that don't occur under normal surface conditions. These pressure-induced changes create unique geological environments that exist nowhere else on Earth. The formation of deep-sea sedimentary layers tells stories that span millions of years, each thin stratum representing decades or centuries of slow accumulation. These layers preserve records of ancient climates, volcanic eruptions, and even cosmic events like meteorite impacts. The deepest ocean basins contain sedimentary sequences that extend back hundreds of millions of years, creating natural archives of Earth's environmental history. Within these ancient sediment layers, microscopic organisms continue to live and reproduce at rates so slow they challenge our understanding of what it means to be alive. Some bacteria in deep-sea sediments may reproduce only once every century or more, existing in a state of near-suspended animation that allows them to survive for geological periods. These organisms represent one of the most patient forms of life on our planet. The chemical composition of water in the deepest places reflects a complex history of interaction with rocks, sediments, and living organisms over vast periods of time. Dissolved minerals tell stories of weathering processes that began millions of years ago, while trace elements record the slow chemical evolution of seawater as it circulates through the global ocean system. The discovery of natural glass formations on the deep sea floor has revealed another way that extreme conditions create unique habitats. When volcanic material erupts into the near-freezing water of the deep sea, it cools so rapidly that it forms natural glass, with properties unlike any terrestrial material. These glass formations provide attachment sites for organisms and create microenvironments with distinct chemical and physical characteristics. The study of how gases behave under the extreme pressures of the deepest places has revealed states of matter that exist nowhere else on Earth. Carbon dioxide, which would form bubbles at surface pressures, remains completely dissolved in the deep water, creating carbonic acid solutions that affect the chemistry of the entire deep sea environment. Other gases form unusual compounds and structures that can only exist under such extreme pressure conditions. The role of the deepest places in Earth's thermal regulation operates through processes so subtle they're nearly invisible, yet so important they affect global climate patterns. The slow circulation of cold, dense water from polar regions through the deepest ocean basins helps distribute heat around the planet, moderating temperature differences and stabilizing climate over long periods. This thermal regulation system has operated continuously for millions of years. Deep-sea hydrothermal vents create extraordinary chemical environments where water heated by Earth's interior emerges at temperatures that would instantly kill most surface life. Yet these vents support some of the most diverse and productive ecosystems in the deep ocean. The chemistry of vent fluids is unlike anything found elsewhere on Earth, rich in hydrogen sulfide, methane, and dissolved metals that would be toxic to conventional life forms. The organisms that thrive around these hydrothermal vents have evolved metabolisms based entirely on chemosynthesis rather than photosynthesis, deriving energy from chemical reactions rather than sunlight. Giant tube worms, some growing over 2 meters long, house billions of symbiotic bacteria within their bodies, creating living chemical factories that convert toxic vent chemicals into nutrients. These partnerships represent some of the most intimate symbiotic relationships in nature. The discovery of these chemosynthetic ecosystems revolutionized our understanding of where life can exist, demonstrating that complex biological communities can thrive independently of solar energy. This revelation has profound implications for the possibility of life in similar environments elsewhere in the universe. particularly in the subsurface oceans that may exist beneath the ice-covered surfaces of certain moons in our solar system. The pressure gradients that exist within deep-sea environments create three-dimensional habitats with dramatically different conditions over relatively short distances. A change in depth of just a few meters can create significant differences in pressure, temperature, and chemistry that determine which organisms can survive in each microenvironment. These gradients create complex ecological zonation that supports remarkable diversity within seemingly uniform deep-sea habitats. The study of how life maintains genetic stability under extreme pressure has revealed unique DNA repair mechanisms that allow deep-sea organisms to maintain their genetic integrity despite the harsh conditions. The high-pressure environment can cause molecular damage that would be fatal to surface organisms, but deep-sea life has evolved sophisticated systems for detecting and repairing this damage, allowing complex life to persist in these extreme conditions. The magnetic properties of deep-sea sediments and rocks preserve detailed records of Earth's magnetic field behavior over millions of years. These magnetic archives reveal that our planet's magnetic field has undergone numerous reversals and intensity changes throughout geological history. The study of these magnetic records provides crucial insights into the dynamics of Earth's core and the processes that generate our planet's protective magnetic field. Some of the oldest water on Earth is found in the deepest ocean basins, where circulation patterns are so slow that some water masses have been isolated from the surface for over 1,000 years. This ancient water carries with it the chemical signatures of past ocean conditions, providing direct evidence of how ocean chemistry has changed over historical periods. The analysis of these old water masses helps scientists understand long-term trends in ocean circulation and chemistry. The formation of natural mineral deposits in the deepest places occurs through processes so gradual they operate on geological timescales. Polymetallic nodules scattered across the deep sea floor grow by accreting layers of metal-rich sediments at rates measured in millimeters per million years. These nodules, some the size of potatoes, may represent tens of millions of years of continuous growth in the stable conditions of the deep sea. The role of deep sea trenches as natural sediment traps has important implications for understanding global chemical cycles. These deepest places accumulate materials eroded from continents and transported by ocean currents, creating concentrated repositories of elements that play important roles in ocean chemistry and climate regulation. The study of sediment accumulation in trenches provides insights into how materials cycle through Earth's surface systems. The discovery of subsurface life within the rocks and sediments of the deepest ocean floor has revealed an entirely hidden biosphere that may contain more living material than all surface ecosystems combined. These subsurface communities derive their energy from chemical reactions between rock and water, creating ecosystems that could potentially exist independently of surface conditions. The existence of this deep biosphere has profound implications for understanding the total amount of life on Earth. The study of how pressure affects the behavior of organic molecules has revealed that the building blocks of life can form spontaneously under the extreme conditions found in the deepest places. Amino acids, the components of proteins, can be synthesized from simple inorganic compounds under the high-pressure, high-temperature conditions around deep-sea hydrothermal vents. This discovery provides insights into how life might have originated on Earth and could potentially exist elsewhere. The acoustic properties of the deepest places create natural sound channels that allow certain types of marine life to communicate across vast distances. Low-frequency whale calls produced thousands of meters above can penetrate down through the water column and be heard in the deepest trenches, creating invisible connections between surface and deep-sea environments. These natural acoustic channels demonstrate how the ocean connects seemingly separate ecosystems. The study of how light behaves in the deepest places has revealed that even in environments of total darkness, subtle forms of illumination may exist. The radioactive decay of naturally occurring elements in seafloor sediments produces extremely faint light, far too dim for human eyes to detect, but possibly visible to organisms that have evolved extraordinary sensitivity to light. This natural radioactive glow represents one of the most subtle forms of illumination in nature. The chemical weathering of rocks in the deepest ocean basins proceeds at rates so slow they're measured in millions of years. Yet these processes play crucial roles in regulating ocean chemistry and global climate. The reaction between seawater and basaltic rocks of the oceanic crust gradually releases minerals that affect the pH and chemical composition of seawater, helping to maintain the chemical balance necessary for life throughout the ocean system. The formation of deep-sea coral reefs in some of the world's deepest places has challenged our understanding of where these ecosystems can thrive. Unlike their shallow water cousins that depend on photosynthetic algae, deep-sea corals derive their energy by filtering nutrients directly from the water. These cold-water coral reefs create complex three-dimensional structures that provide habitat for diverse communities of deep-sea organisms. The role of the deepest places in the global carbon cycle extends far beyond simple storage of carbon dioxide. Deep-sea organisms actively process and transform carbon compounds, while geological processes return some carbon to the atmosphere through volcanic activity at mid-ocean ridges. This deep carbon cycle operates on timescales of millions of years, helping to regulate Earth's long-term climate stability through processes we are only beginning to understand. The study of how time might be perceived by organisms living in environments without daily light cycles has revealed alternative biological rhythms based on chemical or metabolic processes rather than solar cues. Some deep-sea organisms appear to maintain internal clocks based on the slow rhythms of deep ocean currents or the periodic delivery of nutrients from surface waters, demonstrating the flexibility of biological timing systems. The discovery of natural semiconducting materials in deep-sea mineral deposits has revealed how extreme conditions can create substances with unusual electrical properties. Certain sulfide minerals that form around hydrothermal vents have semiconducting characteristics that could potentially support electronic processes in biological systems. These natural semiconductors provide insights into how life might exploit the electrical properties of minerals. The pressure-induced changes in protein structure that allow deep-sea organisms to survive have inspired advances in biotechnology and medicine. Enzymes from deep-sea bacteria can function under conditions that would destroy conventional proteins, making them valuable for industrial processes that require extreme conditions. The study of these pressure-adapted proteins is leading to new applications in biotechnology and pharmaceutical research. The formation of deep-sea brine pools creates some of the most unusual environments within the deepest places. These underwater lakes of dense, salty water have sharp boundaries with the surrounding seawater and their own unique chemistry and biology. Organisms living around these brine pools must adapt to extreme changes in salinity and chemical composition, leading to highly specialized biological communities. The study of how organic matter is preserved in deep-sea environments has provided insights into the conditions necessary for fossilization and the preservation of biological information over geological time. The cold temperatures, high pressure, and low oxygen conditions of the deep sea create ideal environments for preserving organic molecules and cellular structures that would normally decompose rapidly in surface environments. The role of deep-sea currents in transporting heat around the globe operates through a circulation system so vast and slow that it takes centuries for water to complete a single circuit. This thermohaline circulation, driven by differences in water density, helps moderate Earth's climate by distributing heat from tropical regions toward the poles and bringing cold water back toward the equator through the deepest ocean basins. The magnetic navigation systems used by some deep-sea organisms rely on their ability to detect subtle variations in Earth's magnetic field. These biological compass systems allow organisms to navigate across vast distances in the darkness of the deep sea, following magnetic contours like invisible highways across the ocean floor. The study of biological magnetism is revealing new ways that life can sense and respond to physical forces. The chemical communication systems that operate in the deep sea take advantage of the stable conditions and slow water movement that characterize these environments. Chemical signals can persist for extended periods in the deep ocean, allowing for complex forms of communication and coordination that would be impossible in more turbulent surface waters. These chemical communication networks create invisible connections between organisms separated by vast distances. The study of how gas hydrates form and persist in deep-sea sediments has revealed vast reservoirs of methane and other gases trapped in ice-like crystal structures. These gas hydrates exist only under the specific conditions of high pressure and low temperature found in the deep sea, representing one of the largest reservoirs of carbon on Earth. The stability of these hydrates depends on maintaining the precise conditions found in the deepest places. The formation of natural fiber optic systems in certain deep-sea organisms demonstrates how life can evolve to manipulate light with remarkable efficiency. Some deep-sea sponges contain silica structures that act as biological optical fibers, channeling bioluminescent light with precision that rivals human engineering. These biological light guides represent millions of years of evolutionary optimization for manipulating light in environments of total darkness. The discovery of quantum effects in some deep-sea biological systems suggests that quantum mechanics may play important roles in life under extreme conditions. Certain enzymes found in deep-sea organisms appear to use quantum tunneling to catalyze chemical reactions that would be impossible under classical physics, demonstrating that life can exploit fundamental physical principles in sophisticated ways. The study of how sound absorption varies with depth has revealed that the deepest places have unique acoustic properties that fundamentally alter how information can be transmitted through sound. The dense, high-pressure water of the deep sea absorbs certain frequencies, while allowing others to propagate over vast distances, creating natural acoustic filters that affect how marine animals communicate and navigate. The role of the deepest places as natural archives extends beyond their geological significance to include preservation of atmospheric and cosmic history. Dust particles from ancient volcanic eruptions, cosmic debris from meteorite impacts, and even pollen grains from terrestrial plants create layers in deep-sea sediments that preserve records of Earth's environmental history spanning millions of years. The formation of natural crystal structures under the extreme conditions of the deepest places creates minerals with properties that exist nowhere else on Earth. The combination of high pressure, specific chemical conditions, and extended time periods allows for the growth of crystals with perfect atomic arrangements and unique physical properties. These natural crystals provide insights into how materials behave under extreme conditions. The study of how cellular processes adapt to extreme pressure has revealed fundamental principles about the relationship between molecular structure and biological function. The modifications that allow deep-sea organisms to maintain cellular integrity under crushing pressure are so subtle they can only be detected with advanced molecular techniques. Yet they represent the difference between life and death in these extreme environments. The chemical gradients that exist around hydrothermal vents create microenvironments with dramatically different properties over distances measured in centimeters. Temperature, acidity, and chemical composition can change by orders of magnitude within the space of a few centimeters, creating a complex mosaic of chemical environments that support different types of specialized organisms. The discovery of natural metamaterials in deep-sea environments has revealed how extreme conditions can create substances that manipulate energy in ways that seem to defy conventional physics. Certain biological and mineral structures found in the deepest places can control the propagation of sound, light, and other forms of energy, demonstrating principles that are inspiring advances in materials, science, and engineering. The study of how information is stored and transmitted in deep-sea systems has revealed natural information processing systems that operate on geological timescales. Chemical gradients in sediments preserve information about past environmental conditions for millions of years, while the circulation of deep water can transport chemical signals across entire ocean basins over centuries, creating natural communication networks of vast scale and duration. The role of deep-sea organisms as ecosystem engineers extends to their ability to modify the physical and chemical properties of their environment in ways that create habitat for other species. The carbonate structures built by deep-sea corals, the burrows created by deep-sea worms, and the chemical modifications produced by bacterial communities all contribute to creating the complex habitats that support deep-sea biodiversity. The formation of deep-sea mineral chimneys around hydrothermal vents creates temporary structures that can grow to impressive sizes before eventually collapsing under their own weight. These mineral towers, built from precipitated metals and sulfides, provide vertical habitat in the otherwise flat environment of the deep sea floor. The life cycles of these structures, from formation to collapse, create dynamic habitats that support different communities at different stages. The study of how biological clocks function in environments without external time cues has revealed alternative timing systems based on internal chemical oscillations. Deep-sea organisms that never experience daily light cycles have evolved biological rhythms based on metabolic processes, chemical reactions, or the slow periodicities of deep ocean circulation, demonstrating the flexibility of biological timing mechanisms. The pressure-induced changes in the properties of seawater affect not only how organisms function, but also how chemical reactions proceed in the deep sea. Under extreme pressure, certain chemical reactions that are impossible at surface conditions become feasible, while others that occur readily at the surface are suppressed. These pressure effects create unique chemical environments that support specialized forms of metabolism. The discovery of subsurface microbial communities living within the rocks of the oceanic crust has revealed that the boundary between geology and biology is often blurred in the deepest places. These organisms derive energy from chemical reactions between rock and water, creating ecosystems that exist entirely within the solid earth. The biomass contained in these subsurface environments may be enormous, representing a hidden world of life. The study of how nutrients cycle through deep-sea ecosystems has revealed complex pathways that connect surface productivity to deep-sea communities over vast distances and long time periods. Organic matter produced in surface waters can take weeks or months to reach the deep sea, during which it is processed and transformed by organisms throughout the water column, creating a complex web of connections between surface and deep-sea life. The role of the deepest places in regulating global ocean chemistry operates through processes so slow and subtle they're almost imperceptible, yet their cumulative effects over geological time are profound. The chemical reactions between seawater and seafloor rocks, the burial and transformation of organic matter in sediments, and the circulation of deep water all contribute to maintaining the chemical conditions necessary for life throughout the ocean system. The acoustic signatures of geological processes in the deepest places create natural soundscapes that have remained largely unchanged for millions of years. The slow creaking of tectonic plates, the distant rumble of underwater landslides, and the gentle hiss of gas bubbles rising from seafloor vents combine to create a symphony of earth sounds that represents the planet's ongoing geological activity. The study of how life adapts to the complete absence of solar energy has revealed alternative, evolutionary pathways that demonstrate life's remarkable creativity. Ecosystems based entirely on chemosynthesis have evolved complex food webs, predator-prey relationships, and ecological interactions that parallel those of surface ecosystems while operating on completely different energy sources. So tonight, as we drift toward rest ourselves, we can take comfort in knowing that these deepest places continue their patient work in the gentle darkness below. From the quiet chambers of Veriovkina Cave to the profound depths of Challenger Deep, life persists in forms both ancient and eternal, following rhythms older than human memory. Most of our beautiful planet exists in peaceful darkness, where time moves slowly and mystery dwells not as something to fear, but as something to cherish. In these hidden depths, Earth keeps its most sacred secrets, reminding us that wonder and tranquility can coexist in the soft, eternal night that cradles our world. Sweet dreams.